Hi there, Mr. Sutton here. I've got the Pre-Cal Honors 2-3 Extra Practice Number 1 solutions on Rational Roots Theorem. For this problem, we're trying to solve for the complex zeros of this polynomial. So to start, we're going to list out our possible rational roots. Those are going to be the factors of this constant here divided by factors of our lead coefficient. Now, since our lead coefficient is just 1, we don't really have to worry about that part. And it's really just the factors of 24 that we're thinking about. So those would be 1, which is a factor of everything, and these are all going to be plus or minus here. And then we've got 2 goes into 24, along with 3, and 4. Lots of numbers go into 24, but not 5. 6 does though, 6 times 4. And then 3 got paired with 8, and then 12 goes with the 2, and then of course we have 24. So these are all the numbers we're going to potentially try on our calculators until we get one of them that gives us a 0. And then we'll use synthetic division with that number. So let me go to my calculator and plug in the original function here. So I'm on my calculator. I'm going to my y equals. And now I'm going to put this original function in there. I'll just do that off camera. And now that I've got all of that entered in my y equals, let me go to table set just to make sure that my independent is set from auto to ask. That's going to allow me, when I go to my table, to just plug in whatever values I want and get the results. So let's start with 1 and see what happens. Press 1, press enter. We get negative 36. We want to get 0, so let's try negative 1 now. That's negative 10. That's no good. How about 2? That gives me 40, negative 40. How about negative 2 if I plug that in? Ooh, 0. Nice. So we plugged in 1, negative 1, positive 2, and finally, that should say positive 2 there. There we go. And then finally, we plugged in negative 2, and that gave us 0 from our calculator. That means that when we actually plug in negative 2 with synthetic division on this thing, we're going to get a remainder of 0, and that's going to allow us to factor this polynomial into something a little bit smaller. So let me write out my coefficients now, doing some synthetic division. We've got 1, another 1 for the x squared, and then negative 14, negative 24. And since negative 2 is my number that gave me 0, I'm going to use that as my box number here. Let me set up my, my line there, and let's start this process. So bring down the 1, times negative 2 gives me negative 2, plus 1 gives me negative 1, times negative 2 gives me 2, plus negative 14 gives me negative 12, times negative 2 is giving me 24, plus 24, negative 24 gives me 0, which is what we expected. So this means that I can factor my polynomial into x minus the box number. So that's going to be x plus 2. And then these numbers down here are the numbers for our quotient. So we're going to have a 1 for 1x squared, one exponent lower than we started with, minus 1x minus 12. And we'll say all of that equals 0 because we're trying to find the zeros when we find the roots. So this x squared minus x minus 12 piece, we can actually factor this a little bit further. We need numbers that multiply to negative 12 and add up to negative 1. That would be positive 3 and negative 4. So we can break this into, we'll bring down the x plus 2, and then we'll have x plus 3 and x minus 4. All of that equals 0. And now just going through and zeroing out each of these, we've got x equals negative 2, negative 3, and positive 4 for our answers. For this problem, we're wondering which of these factors below are actually factors of the polynomial f of x here. And it could be more than one of them. Select all that apply. So there's a couple ways to do this. One way to do this would be to, if you have a calculator available, just plug in whatever zeroes out each of these factors and see if it gives you 0 for the polynomial. You could do that without a calculator. It's just a little bit more work. Another way to do it would be to try to find one of the factors and then use a little synthetic division to break things down to get the other factors. So I'm going to start with the factor, let me see here. Let me try this x minus 1 factor. The reason I'm going to try that one first is because it would give me a box number of 1 with synthetic division. And 1 is like the easiest thing to do synthetic division with. So writing out my coefficients here, we've got 1 for the x cubed minus 7 plus 14 minus 8. Again, I'll use a box number of 1. I could have started with -1 to represent the x plus 1, but 1 is just easier to use. So we've got 1 that's coming down here, times 1 is 1, plus -7 is -6, times 1 is -6, plus 14 is 8, times 1 is 8, and plus -8 gives us 0. So that one actually works, which means that x minus 1 is a factor of our polynomial. Sweet. We can factor it then into x minus 1 times whatever this quotient comes out to. So this is going to be 1x to the second power because we started with third power and we always go one lower after doing this division. So 1x squared minus 6x plus 8. And at this point we're going to try to factor this x squared minus 6x plus 8. We hope we can factor it. We need two things that multiply to positive 8 and add up to -6. So -2 and -4 would do the job. So that's x minus 1, x minus 2, x minus 4. Looking at our answer choices, that means we have choices B, D, and F. On this problem, I'm trying to find the complex zeros of this quartic fourth degree polynomial. We're going to start by finding the possible rational roots, the PRR list, and we'll start using those in our calculator to see if we can find any zeros right off the bat. All right, so for possible rational roots, that's going to be factors of my constant 75 divided by factors of my lead coefficient 9, and these are all going to be plus or minus. So we've got 1 as one of the factors of 75, and then 3 goes into 75, 25 times. We've also got 5 going in there. And what's the next number after 5 that goes into 75? Well, 5 divided into 75 is 15, so I think that's the next number that goes in there, followed by 25, that goes with the 3, and of course 75 itself. Now the factors of 9 are a little bit easier. That's just 1, 3, and 9 down there. But now I have to actually write out the fractions individually. So we've got all of these numbers in the numerator divided by 1. That'll give me my first list of 6, well, actually 12 if you count the pluses and minuses, possible rational roots. Now we have to take all these numbers up here and divide by 3. So we've got 1/3, we've got 3/3, but that's just 1, we already wrote that. 5/3 is new, 15/3 is just 5, already got it. 25/3 is new, and 75 over 3 is just 25. Next, we divide all these things by 9. So we have 1 over 9. 3 over 9 is just 1/3. We already have it. 5/9 is new. 15 over 9 is 5/3. Already got it. 25 over 9 is new. And then 75 over 9, we can reduce that by 3 to 25/3, which we already have. At this point, we're going to start plugging these numbers into our calculator, into this polynomial. And we're going to do that until we get a 0. Then we'll use that to use some synthetic division and break this thing down a little bit. So let me go to my calculator now. So here's my calculator. I'm going to go to my y equals, and I'm going to enter this big polynomial in there. I'll do that off camera just to save us some time. Okay, so I entered that whole polynomial into y1. There's the tail end with the plus 75 there. Let me now go to second window, and I'm just going to make sure that independent is set to ask so that when I go to second graph and go to the table, I can now plug in whatever x values I want and get the y values back. So let me start by plugging in the x value 1. I always start with positive 1. So plugging that in, we get the y value 272. So that's not what we want. We want to get 0 back when we plug in a number. So let's plug in -1 next. And that does give us 0. So we didn't have to plug in too many of these. So f of 1 didn't really help us, but f of -1 gave us 0. So I'm going to use synthetic division on this polynomial now, using -1 as my box number. Writing out my coefficients, I've got 9, 36, 52, 100, and 75. And we'll do our little line here, and now a box number of -1. We've got, bring down that 9 to start us off here. -1 times that is -9. Plus 36 is 27. Times -1 gives us -27. plus 52 is 25, I believe, times negative 1 is negative 25, plus 100 is 75, times negative 1 is negative 75, plus 75 is 0. Awesome. So this means that we can now factor this polynomial into x minus the box number, x plus 1, times the quotient that we got down here with these numbers. This 9 represents 9x to the third power, because we started with the fourth power, so now we're down to the third power with our quotient. So 9x cubed, plus this is 27x squared, it goes down 1 each time, plus 25x, plus 75. And we're going to set that all equal to 0, because we're trying to find the zeros, and we're going to continue this on the next slide. So here we are, continuing our problem. Where we left it off, we had factored our polynomial into this expression here. So we're going to keep going. Now, when I get my PRR list, it's actually going to be the same list as before, but I am going to look. I'm still doing factors of 75 over factors of 9, so I still have the same long list of things that we had on the last slide. We're going to test these out now using just this 9x cubed part of our polynomial, because that's the thing that we're trying to break down a little bit further. So let me go back to the calculator and enter just the 9x cubed stuff, which I'm going to call g of x just for our purposes here so I can refer to it quickly. I'm going to put g of x in my calculator as y2. So here I am in my y equals. Again, I put g of x as my y2 here, and there's no reason to delete y1 just yet. Might be helpful to keep it around just for reference. Let me go to second graph now, to table, and I can see what happens if I plug 1 and negative 1 into my y2, into this g of x. It doesn't give us 0 for either of those, but it was worth at least looking at negative 1, because if a 0 works once, it can work again. If a 0 doesn't work the first time, it'll never work. So 1 we didn't really have to worry about anyway. But I have a few other numbers I want to plug in now. So next number on my list I want to plug in is 3, positive 3. Let's see what happens if I plug that in here. We do not get 0 for y2. That's what we're looking for there, although either one should give us 0 at this point. Let's try negative 3 and hope for the best. And that does give us 0. So g of negative 1 didn't help, but we had to look at it. G of 3 didn't help. G of negative 3 gave us 0. So now we will do synthetic division on just g of x here using negative 3 as the box number. So my coefficients now, we've got 9, 27, 25, and 75. And our box number now is negative 3. Let's start by bringing down that 9. Times negative 3 gives me negative 27, and we've already got 0 down there. Times negative 3 is 0, plus 25 is 0. I love 0. Times negative 3 gives us negative 75, plus 75 is 0. So we've got this thing factored down a little bit more. Don't forget the initial factor we had of x plus 1. That's still there. We also now have x minus negative 3, or x plus 3. And this 9 now represents 9x squared, because it was the x cubed that we were breaking down. So that's one exponent lower, 9x squared. This 0 represents 0x, so we don't have to write that. We do have to write the plus 25, though. And all of this still equals 0. Okay, so this 9x squared plus 25, we have to go a little bit further on that one. I'm going to set that equal to 0 and solve it now. I can start that process by subtracting 25 from both sides and then dividing by 9. So we've got minus 25 over 9 if we do that. And then I'll just square root both sides. So we've got 5 over 3, a plus or minus. And since we have a negative here, we have an I coming out as well. So this is plus or minus 5i over 3. Going back and officially writing all my answers from left to right, the first parentheses gave me x equals negative 1. Then we have x equals negative 3. And then finally we have our two complex roots of plus or minus 5i over 3. That's a total of 4 answers, which is what we expect because we started with a 4th degree polynomial. For this multiple choice question, we have this function defined as f of x here, and we have this mystery constant c in here that we're trying to find. We're given that our graph intersects the x-axis at 3 points. They gave us 3 zeros. Based off this, we want to find the value of c. So two of these points kind of make sense, negative 4, 0, and 1/2, comma 0. This p comma 0 is kind of weird, not really sure what that p is all about, but it's not extremely helpful. So how can we find c? Well, c is one of three unknowns in this expression they gave us, in this equation. We also don't know x and y, or at least those are variables. If we could plug something in for x and y, then c would be the only thing we didn't know in this expression. So it turns out we can plug something in for x and y. We know that for this polynomial, when x equals negative 4, for example, we have a y value of 0, because they gave us that point. So if we plug in negative 4 for x and 0 for f of x, or y if you want to call it that, that'll just leave c as the only thing we don't know. So let me go ahead and do that. We'll have 2 times negative 4 cubed, and I'll put that in a parentheses, plus 3 times negative 4 squared, plus, this is going to be c times negative 4. We still have a plus 8, and all of that should now equal 0, because that's what y is when x is negative 4. Now we just have to simplify and solve this thing. So we've got negative 4 cubed is going to be negative 64, times 2 is negative 128. 4 squared, negative 4 squared is 16, times 3 is 48, so we're adding that. We've got negative 4c, still have a plus 8, still have an equal 0. Combining stuff on the left side, negative 128 plus 48, that's going to be negative 80, and negative 80 plus 8 is negative 72. I'm going to add that 72 over to the right side. And now if I divide both sides by negative 4, I believe that is going to be 18, negative 18, that c equals. So that gives us answer choice A.